Happy Tuesday. Final unit. Exciting and sad. I think it's only like 3 weeks left, too. What we're going to be doing is essentially taking everything we've learned in calculus up to this point and throwing it all together into one chapter. Vector analysis, or vector calculus, called the same thing. We're extending our notion of vectors. Right, so remember we looked at a vector valued function, right, R of t. And it was, what we looked at was 3 component vectors. But it could have been, or 3 component functions, right? But it could have been like 4 or 5, whatever the dimensions are. That was single variate. We just got done studying multivariate functions. So wouldn't it be possible to have a vector whose components are multivariate functions? So essentially a multivariate vector function. It's called a vector field. Again, you can have 2 dimensions, 3 dimensions, 8 dimensions, however many dimensions. Funny thing is, so we have a 3-dimensional vector field. That means we have 3 components. That doesn't necessarily mean that each component has to be 3 variates. It could be the 2 variate 3-dimensional vector field, which is odd. Let's call it XY. All right, so this would be an example of a 2-dimensional vector field. F of XY, G of XY. F and G are the component functions. But we can do partial derivatives on this. While we don't really ever do it, I guess you could integrate. I guess you could do a double integral on that. And it would just be the double integral of each component. We're going to study 2 new types of integrals. Those are the ones that we typically use for vector fields. They're line integrals and surface integrals. What a vector field does is for each point xy, it gives you a vector. So plotting a vector field is interesting because there's theoretically an infinite number of vectors. Right, a vector where the xy, your point, is the initial point. Right, and then the terminal point is whatever it evaluates out to. We are not going to be doing that by hand. Several types of vector fields. This one is called a spin field. You're going to see why. One of the most common vector fields is an inverse square field. Gravity is an inverse square field. Electric force is an inverse square field. Magnetic force is an inverse square field. So we have vector plot for two-dimensional vector fields, and then we have vector plot 3D for three-dimensional. Remember when we looked at parametric plot, you had to do each component, right? So we're doing the same thing here. Our first component was negative y divided by square root x squared plus y squared. Oops. Then it was what? X over the same thing. Been a while. What happens? This is technically all you need. Right, the rest of it's just options and settings. Yeah, see, I don't like that. So that's what it would give you. That's not at the origin right now. Perfect. So let's adjust some settings. Turn the frame off. Turn on the axes. Go ahead and label them. Right. It'll give us this now. Oh dear, I think they've changed something since I last looked at this. Oh boy. For some reason that fixed the coloring. Okay. I just set my vector points to regular. I mean, that doesn't really matter. If I actually look up what vector points does, like I said, it's been a while. I think it's how to choose the points. Yeah, it's where to draw them. Right, so it's where to choose the initial points. Or how to choose them. At 7, 9, I have no idea. And so you can leave it like that. I'll just always stick to setting regular.
Was there any point to what the colors meant for eventually?
If I had to take a guess. Well, actually, here I don't know. Sometimes the color represents magnitude. But this should all be unit. This is a unit vector field. So I don't know what the colors represent here. Right, because they're not going to obviously draw them to scale. So they kind of color code it if, you know, to represent different lengths of the vectors. All right, so this is why it's called a spin field. Spinning. However, we were asked to plot it on the circle x squared plus y squared equals 4. I'm going to leave this. So we need a region function. The function of x and y right, since we're plotting it on the circle, what they mean is they want it over that entire region of the circle. So that's why it's 0 less than x squared plus y squared less than equal to 4. Notice we're not including 0 because the square root of x squared plus y squared is in the denominator. All right, now, if this is where we stop, that's what it'll give us. So again, that's perfectly fine. All right, you have the region included. You can then start to mess around with the boundary and the region, right? You can change the colors, all that. For my preference, so region boundary style is going to affect the line, right? The boundary of the region. So you can set it to dashed, bold, change its color, whatever. I don't want one. And then the region filling style, that's going to dictate how it's shaded. Right, so again, you can change that color. Then you can change the darkness of the shading. For me, I don't want it. I'm going to turn it off. And so there's the vector field. There's our spin field on the circle x squared plus y squared equals 4. Three-dimensional radial field. And so radial field is another type of vector field. I don't have to type that out 3 times. So I'm just going to define R to be that square root. Then our vector field is just X over R, Y over R, Z over R. Let's go -5 to 5 all the way around again. Let's see what that gives us. Right, again, that is all you need. And that is what it would give us. Doesn't really show what's happening now. Let's do axes label. That kind of shows you what's happening. Again, it's a unit vector field, right? All of the resulting vectors are going to be unit in length. And they're pointing away from the origin, right? So it's kind of like it's radiating out from the origin. That's why it's called a radial vector field. You can also have it kind of being attracted into the origin. Right now, I did set other options. I think these other options make it easier to see. I did light blue and then just so it's not as dark. Light blue. I wonder how this would look. Actually looks better in my opinion. Maybe you can mess around with it. What would happen if I don't do the color function? Yeah, say if I don't do the color function, it's gonna not change anything. So I have to turn off the color function. Okay. But you get the general gist of vector fields. Same thing with vector valued functions. The domain of a vector field is the union of the domain of each component function. Right? Makes sense, right? Because you can't have a vector field where one component's undefined. All components have to be defined. Right, in the case of these two, why there's a parenthesis there. No idea. That's odd. Right, in the case of these two, would be everything but the origin, right? There's no way x squared plus y squared is going to give you 0 unless it's the origin. And there's no way x squared plus y squared will ever give you a negative. Same thing with x squared plus y squared plus z squared. So it's just everything except for the origin. We're given a vector field. We're asked to find what? 4 partials? All of the second order partials, right? So here's an example of it's a 3-dimensional vector field, but it's 2-variate. Well, we're obviously going to need the first order partials, right? I'm going to represent it in component form for right now, and then at the end, I'll convert it back. I just find it easier to work in component form. Well, how did we take the derivative of a vector function? We're given r of t, we wanted r prime. So don't you think it's the exact same thing for partials? Yeah, just take the partial of each component. What is the partial of the I component with respect to x? What about the j component?
Y equals the xy minus y cosine x.
And the k component.
Two x cosine y.
So there'd be partial with respect to x. Also write out the partial with respect to y. I component with respect to y. J component. K component. So there's the first order partials. Let's find AXX, and at this point, I'm going to write these in the IJK form, right? Because these are what we're actually looking for. Second order partial with respect to x. What's the I component?
Y minus 12 times x squared.
J component. I think you looked at AY when you did the partial with respect to x.
Be y squared e to the xy plus y sin x. Say that. Say that.
Right? Y squared e to the xy minus or plus y sine of x, right? That's the J component. What about the K component?
Cosine y. Or I mean 2 cosine y.
So there's AXX. Which one do I want to do next? Let's just go in order. They want AYY next. I component. The what?
Zero.
Don't technically need to write it, but I'm gonna write it out anyway. What about the J component?
Square times e to the xy.
And what about the K component? And so there's AYY. There's a theorem when we looked at multivariate functions, right? When we studied partial derivatives. It's called Clairaut's theorem. Remember what that said? It was an extremely useful theorem.
What did you say the theorem was for again?
When we studied partial derivatives.
Isn't it the theorem that like the derivative of a of partial derivative xy is the same as a partial derivative of yx?
The order in which you take the partials does not matter. Well, since we're taking partials by component, and each component is a multivariate function, Clairaut's theorem would apply to each component, right? Which means it applies overall. We have not lost that property. The order in which you take partials does not matter, meaning your mixed partials are equal. So AXY and AYX are going to be the same. I am going to use that, so I only have to calculate one more. All right, so we're going to look and we're going to see which one would be easier. X with respect to Y, or X first then Y, or Y first then X. Well, the first part doesn't matter. That's going to be product rule regardless. And honestly, the second term of that middle component, that's not going to matter. I don't think it really matters in this case. They're both going to be fairly simple, right? So pick one. You want to do XY or YX? What was it?
Y.
So we're going to look at Y. We're going to look at A sub Y, and we're going to take that partial with respect to X. I component. J component. You missed the term. You're missing a term in your derivative. Take a look at the first term. How do you read that? Which means X times e to the XY, right?
Yeah.
X is clearly a function of X. E to the XY is also a function of X, isn't it? So that's product rule. So your missing term would be e to the XY, right? And then what about the K component?
Negative 2x sine 1.
It is left as an exercise that if you take the partial of AX with respect to Y, you get the exact same thing. Pretty sure the intent here was to have us use a product rule. Specifically the scalar product rule. Right, so we'd have to take the partial with respect to phi, then multiply that by f, add it to phi times the partial with respect to f for each of the three. However, we don't need it. Because we can just distribute the phi in, right? Scalar multiplication. Oh yeah, all those vector operations are still valid. Scalar multiplication, vector addition, vector subtraction, dot product, and cross product. And they all still behave the exact same way. Right? Because ultimately, a vector field is just a vector, right? Still a vector. It's just multivariate. So I'm going to go ahead and distribute the phi. I'm going to do the scalar multiplication first, and then take the partials. Then we don't have to worry about the scalar product rule. Been a while. Scalar multiplication. How did we do it? Bless you.
Not just the dot product.
So that's dot product is also called scalar product. We're doing scalar multiplication. Don't you just multiply each component by the scalar? So we're going to get what? X squared, y squared, z squared for the first. Negative x squared, y to the fourth z for the second. Xy cubed z cubed for the third. Now we're looking for a third order. Twice with respect to x, once with respect to z. Remember, the order does not matter. So you kind of want to look at this and see, would there be a particular order that gives you an advantage?
Is like have the x's be right next to each other so that maybe you can get some of the constants like really rid of each other, maybe.
So you say x's next to each other
Take them consecutively.
concurrently. Do you want to do them before z or after z? Notice what's going to happen to the third component if you do it with respect to x twice. Goes to 0. Which makes taking it then with respect to z, you only have to do 2 components instead of 3. In this case, because of how easy the functions are, it really doesn't matter. So if we do it with respect to x, what are we left with?
Squared.
Z squared?
Squared there. Five cubed c cubed.
Do it again with respect to x. What we'll wind up with, right? Right, now remember, when writing it in Leibniz form, the order in the denominator is read right to left. So this is how we would write the order that we just did. Clairaut's theorem says that's the same as the order that we wanted. So I'm just going to specify that they are indeed equal. Now take the partial with respect to z. That's what we're going to wind up with. We're not done. They wanted us to evaluate it at a point. So we need to evaluate that at the point 2, -1, 1. Well, evaluating a multivariate function, same as evaluating a vector valued function. Right, same as evaluating a function. Everywhere we see an x, we're going to put a 2. Well, there are no x's. Perfect. Everywhere we see a y, there's going to be a -1. Everywhere there's a z, there's going to be a +1. Or -2, 0. We are now going to look at my two favorite operations in mathematics. Divergence and curl. By the way, without these two operators, none of this would be possible. Now I'm drawing a blank on what those equations are called. It's not Gauss. I believe I'm drawing a blank. One of the most famous equations from electricity and magnetism. Maxwell, that's it. That's the guy. Maxwell's equations. Which actually only one of the four is his. I think Gauss has two of them. And then there's a Faraday in there. But Maxwell is the one who kind of saw how they're related. So he got credit for it. Maxwell's equations governs electricity and magnetism. It also shows us that, also shows us that we can get magnetism from electricity and vice versa. Those four equations essentially govern all the laws of electricity and magnetism. Which, of course, is what allows technology to exist. Actually, even without those four laws, there wouldn't even be light. There's actually two forms of Maxwell's equations. There's the differential forms, which are divergence and curl related, and then there's the integral form, which deals with line integrals and surface integrals, which we have yet to study. It's represented two ways. Div of f, red divergence of f. Or del dot f. Right, partial of the first component with respect to x plus partial of the second component with respect to y plus partial of the third component with respect to z. The advantage of writing it as del dot f is that that equation becomes obvious. And remember that nabla is the del operator. Writing it as del dot f, you can kind of see it this way. Remember how you do dot product? It's just the sum of the product of the individual components. Right, so D, instead of dot, right, instead of product, what we're doing is it's operations. Right, so first component operates on first component, second component operates on second, third operates on third, add them together. Right, so it's kind of like a product, but it's not really a product. Just like this is not actually dot product. And if it was dot product, then we'd be able to write this, right? Because dot product is commutative. That makes no sense. Right, so difference between operators and actual products. Right, this would be like writing this. That makes no sense whatsoever. Right, because ddx is an operator, it has to operate on something. Again, that'd be similar to this.
This is just like the symbolic issue.
Yes.
It's not like changing more.
No, it's
Make sure you write
symbolic.
it like
Yes.
that.
Right, because you have to keep in mind that writing it this way, this is not a dot product, right? We're making it look like a dot product because it makes it kind of easier to understand how we're doing it, but it's not a dot product. This is an operation. Right? That's why some people refuse to write it this way as del dot f. just to avoid the confusion of dot product. So you'll probably, I think your book doesn't use this representation. I think your book sticks with divergence of f, div of f. Right, I'm gonna actually fully write out what we're doing this time. And then, unless it's a theory problem, I will not do it again. All right, so divergence of f. Partial with respect to x of the first component. X squared, z squared. Plus partial with respect to y of the second component. Negative 2y squared, z squared. Plus partial with respect to z of the third component. X, y squared, z. Divergence is 2x squared minus 4y squared plus xy squared.
That expression that we just got is called the divergence.
It's so this is the divergence of f. The actual physical geometric interpretation of divergence is considered later. I believe I discussed that when we look at divergence theorem. Same thing with curl. I discussed the interpretation of curl when we study, I think it's Stokes' theorem. Well, remember, we already looked at the del operator, right? We did it back with directional derivatives. We studied the gradient. Remember that? The gradient's actually a vector field. And if you take the gradient of a function, don't you get a multivariate vector? This is called the gradient field. So what we're going to do is find the divergence of the gradient field of 6x cubed y squared z. And again, it doesn't have to just be 3 variables. It can be however many variables. By the way, gradient fields have another important property, which we will look at. I think it's next week we look at it.
Present these graphically, or is this like a fourth type two?
Well, gradient fields?
Yeah.
Well, gradient field in this case, this is three-dimensional, isn't it? It'd be partial x as your first component, partial y as your second, and partial z as your third. So however many variables the function, it's a function of, that's how many dimensions the gradient field's going to be. So the gradient of 6x cubed y squared z first component, partial with respect to x. Second component is the partial with respect to y. And the third is the partial with respect to z. Now the divergence. Partial of the first component with respect to x. Plus partial of the second component with respect to y. Plus partial of the third component with respect to z. Which is a goose egg. There's our divergence. Nabla squared is called the Laplacian operator. Okay. So if we looked at the Laplacian of a function, it'd be the second order partial of that function with respect to x plus the second order partial of that function with respect to y plus the second order partial of that function with respect to z. What we're going to do is prove that for any function psi, the Laplacian of psi is the same as the divergence of the gradient field of psi. Well, gradient of psi, right, would be partial psi, partial x, partial psi, partial y, and then partial psi, partial z. Divergence of that. Partial x of the first component. Partial y of the second. Plus partial z of the third, right? That gives us the second order partials. Factor out the psi, and I'm using factor very loosely here. And we get the Laplacian of psi. So you can do either one. You can either find the gradient field first, then take its divergence, or you can just go right into the sum of the second order partials. On Thursday, we will look at a partial differential equation known as Laplace's equation, and then look at curl. All right, that'll finish that up. Then there'll be a quiz, and then we'll start line integrals. There are two types of line integrals: line integral of a scalar function and line integral of a vector field. We'll look at both. See you all on Thursday.
Way to check